Hello everyone, my name is Chih-Chun Hsu. I'm an astronomer at Northwestern University. Today, I'm going to talk about a very interesting discovery of an ultra-cool dual binary star system. And not pretty far along, we're just back in 1995 when we start to see there's actually an extrasolar planet outside of our solar system. Ever since then, until today, we have discovered more than 5,000 different exoplanets outside of our sun. And here's a very popular image that shows that we can actually take the photo in front of the other extrasolar planet system, HI 8799 planets, that's labeled in B, C, D, E on this picture. And the star is so bright, so we have to block away its starlight so we can see this light from all of these planets, which is pretty amazing. And there's also another very famous exoplanet system called TRAPPIST-1. And this system is famous because it has 7 Earth-sized planets. And what it makes even more interesting is because 3 of these planets might have liquid water, which is what we define as habitable from astronomy perspective. So that basically means we can find the liquid water on these planets, and on one day, human beings can travel and live there. And if we look at the night sky, here's a beautiful picture of the Milky Way, which is in the center. And there's little tiny dots are different stars in our Milky Way galaxy. If you start to sort based on their brightness and the temperature, we can see they actually have some orders. If we plot this as on this busy diagram, I want to just focus on the brightness versus the temperature. And these little dots are different stars in terms of different temperature and brightness. Our sun is not so special. It's about in the middle. You can see it's roughly has a size like and the right temperature. And what I study is the object called M dwarfs that's on the bottom right. These are only 10% of the masses of our sun and only 50% of the temperature of our sun. So these are pretty faint and tiny. And the reason why I focus on these objects are because these are like commonly having exoplanets. Per M dwarf, each M dwarf might have 1 planet on average. And that includes the TRAPPIST-1 planet system I just mentioned. And because these objects are so tiny and small, so we have to use pretty large telescope, not the tiny one. We have to use the 10-meter. This is the Keck telescopes that's in Mauna Kea, Hawaii. And this is me with my colleague taking the data back in 2017 when I was in my graduate school. And just to show the methodology that I take the light or the infer their motion, the phenomenon is actually called Doppler effect. And we're in Evanston, so it's actually pretty common to have the sirens from these ambulance and police cars. When it passes through and moves away from you, you see the tone or frequency goes higher and lower. That's called the Doppler effect of the sun. And that's the nature of the wave. And the same technique applies for the light. That's because when we see there's a star and there's a companion, either another star, which we call the binary, or the planet, when they move around each other, they change in velocity and also change the spectrum or the light of the system. So we measure at different time, we can see it start to shift in terms of this spectrum back and forth. And here today, I'm going to show you the interesting discovery. This is a spectrum of the M dwarf called LP41353. What makes it interesting is from its spectra. So this is the brightness versus the wavelengths. And in the beginning, when we see the spectrum, these 3 different lines appears to be the single star. But after an hour, if we retake the spectrum, the light starts to split. That's because this is indeed a binary. If we take another spectrum after the next hour, it's been further split away. And we can actually measure how fast it's been changing and then infer how fast they're orbiting around each other. And as a result, the orbital period is actually 17 hours. This is actually a record breaker from all of the systems we found in M dwarfs that has been closest in this mass regime, or we call the shortest period ultracooled dwarf binary system. And this is interesting because it has the same temperature, same size as TRAPPIST-1. But this is the first system that we found that can be so close that's being closer than any other planets of a TRAPPIST-1. The question becomes if these systems can have planets. And if so, how frequent are they? Is it habitable? So here's my key messages I want you to take away. So first, there's a very interesting ultracooled binary star system with the orbital period of only 17 hours. Second, we want to learn if this kind of system is frequent, and if so, it can host planets, and can it be habitable? Finally, we have scenarios of how this system can evolve into the current stage, and please scan this QR code if you're interested. It's been nicely covered by Northwestern University. Thank you so much.